Hi everyone, my name is Xiaoyan Zhang, and I'll be talking about adaptive correspondence scoring for unsupervised image registration. This is work done with John Stendal, Larry Stape, Alba Sunusis, Alex Guan, and James Duncan. The goal of image registration is to spatially align two images by estimating the displacement between a source and target image pair. The displacement is then used to apply a spatial transformation to the source image, resulting in a aligned or warped version of the source. Obtaining ground truth displacement for each pixel is extremely expensive. A commonly used unsupervised objective is usually designed in a way that minimizes the reconstruction error between the warp source and target. The feasibility in minimizing this objective relies on intensity constancy between the two images during training. This raises a question: is the intensity constancy the perfect assumption? Let us take a look at the following example. Assume that we have two images, a source and target, with a red box to highlight the regions that are visually corresponding to each other. A desired training process will be, as the training loss reduces, the accuracy, for instance, measured by the dye score between anatomies, should be improving. Let us assume at epoch t, where the optimization drives the warped image at a reasonable local minimum, which is evidenced by the visual resemblance between two images. However, the error map is still non-zero, especially in the highlighted red box. In the next epochs, the optimizer will drive the displacement estimator towards undesired local minimum, as shown in the highlighted red box, deviating from the ground truth due to the noisy gradients. This is due to that the error residuals between the warp source are currently dominated by regions with no correspondence and are reconcilable. In this case, the intensity constancy assumption is violated, and the further optimization results in performance degradation. To address this, we propose to reweight the error residuals with a predictive adaptive correspondence scoring map. By doing so, we get a smoother optimization and reduce the influence of these outliers, leading to an improved performance. Our proposed framework first estimates the displacement from source and target image pair. We then apply spatial transform to obtain the warp source image. Before computing the error residuals, we estimate the correspondence scoring map from the target image and then adaptively weight the error residuals for gradient-based optimization. In order to correctly estimate the correspondence scoring map, we introduce three modules. First, we have the unsupervised correspondence scoring loss, which aims to encourage the scoring estimator to assign a lower score to regions with high error residuals. We further regularize the scoring map to avoid the trivial solution of not all zeros. Finally, we propose a momentum-guided adaptive weighting to reduce smoothness early for exploration and increase it later for convergence. More details can be found in our paper. Qualitative visualization of our proposed approach invokes some of architecture on ACDC and CAMUS validation sets. The third column exhibits successful matching, but the error residuals in the fourth column still reveals residuals. Our predicted scoring map in the fifth column identifies and prevents the drift of displacement estimator, as demonstrated by the weighted error in the last column. Our proposed matrix approach based on voxelmorphic transmorph outperforms the baselines in ACDC and CAMUS datasets. More results can be found in our paper. One potential application of our proposed approach would be doing cardiac strain analysis. In the above figure, we test our proposed approach on a clinical 3D echocardiography sequence from a patient. After estimating the displacement from end diastole frame to end systole, we compute the green Lagrangian strain on each voxel. We showed that our derived strain can be helpful in identifying myocardial infarction, which is evidenced by the matching with patient's clinical record, indicating akinetic septal and inferior walls. In conclusion, we identify the limitation of the widely used intensity constancy assumption in unsupervised image registration. We address this by proposing an adaptive correspondence scoring framework during training, and our proposed approach can be plugged and played into existing frameworks with no extra cost during inference. Please visit us in poster section. Thank you very much for listening.